All right, so today we're going to be talking about expected value, which is a systematic way of determining the expected net gain or loss of a probabilistic situation. What does that mean? Okay, so expected value essentially is talking about what would you think is going to occur? What should you bet if you're playing if you're gambling, or should I buy this lottery ticket, or what can you expect to happen in any given situation? Okay. There are gains, there are losses, you can lose money, you can gain money. Okay, so what expected value is, um, if you just look at it in terms of a table here, right? Whatever this first payout is, let's say you gain money, well, that has a specific probability of occurring. Okay, let's say you get a different amount of money. Well, that has a different probability of occurring. So however many different possible outcomes there are in this experiment, each of them has their own probability and each of them has their own payoff. Okay, so the expected value then is the sum of each payoff times its probability. Okay, so this one times this one, plus this payoff times this probability, plus this one times this one, on and on and on, until you've covered all possible outcomes. Okay, now this is going to be, it's going to come out as just a number. All right, if it's a positive number, that usually means good things. All right, if it's a negative number, that usually means bad things. And if it's zero, then the game is what we would call fair. Rarely are you going to be given a fair situation, but you never know. Okay, so for example, um, totally fictitious situation going on right here. Suppose the world famous gambler Senor Stampstato proposes a game to you. Okay, you roll two fair dice. If the sum of the dice is 8 or more, Senor Stampstato wins $2. If the sum is 7 or less, he pays you $1. All right. So find the expected value of each roll of the dice in this game. And what does it mean? Okay, so on the surface, let's just think about this. Is this fair? Would you play this game? Um, he's winning $2 every time he wins. You only win $1. Okay, well, now right away that might not sound fair, but 7 or less has more possible outcomes than 8 or more. Okay, so now maybe does that balance out? Well, that's what expected value tells you. Is that fair? All right, so let's make a little chart here. Okay, what happens? Senor Stemstato wins $2 if he rolls an 8 or more. Okay, so 8 or more, you lose $2. Okay, so in terms of fairness to you, you are losing $2. Now, what is the probability of that? We'll figure that out. Okay, 7 or less, you are gaining $1. Okay, so now what we have to do is we have to figure out the probability of actually rolling 8 or more or 7 or less. Okay, well, it's not quite as easy as simply, 8, 9, 10, 11, 12. So 5 out of 12, okay, it's not that easy. All right, so let's just think about this. How can we roll an 8? How many ways are there to roll an 8? Well, you can have a 4 and a 4, you can have a 5 and a 3, or a 3 and a 5. Those are different. 6 and a 2, or 2 and 6. Okay, there's 5 different ways to roll an 8. Okay, to roll a 9, 5 and 4, 4 and 5, 6 and 3, 3 and 6. Okay, there's only 4 ways. To roll a 10, you either have to have a 5 and a 5, a 6 and a 4, or a 4 and a 6. There's only 3 ways. Gee, I wonder if you see a pattern. For an 11, 6 and 5, 5 and 6. There's only 2 ways to roll an 11, and for a 12, you have to roll double sixes. There's only 1 way. Okay, So there's 36 possible outcomes when you roll 2 dice, 6 from the first, 6 from the second. Fundamental counting principle, multiply them, 6 times 6 is 36. Okay, so 8 or more, you have 5, 4, 3, 2, and 1. That's 15 out of those 36 as the probability. Okay, let's make a little table here. All right, let's just go to that. Well, if there are 15 out of 36 ways to roll 8 or more, since there's only 2 possible, I mean, you can list them out like I did here, or you can just trust me and say that there are 21 out of the 36. 15 plus 21 is 36, and there's all of your possible outcomes. Okay, so the probability of getting 7 or less is 21 out of 36. Okay, so let's see if this is fair. So expected value would equal that negative 2 times the 15/36 plus the positive 1 times the 21/36. Okay, again, A off times probability. A off times probability. Okay, when you multiply that all out together, right? Negative 2 times 15/36 plus 1 times 21/36. Okay, so the expected value is negative 0.25. What does that mean? Well, because we made this in terms of like you winning or losing, and the answer is negative, what does that mean? It's bad. Okay, there's a reason why this world famous gambler, Senor Stemstato, offered you to play this game, because it favors him. He's winning more money on his rolls than you are on your rolls. Okay, so it's not fair. But if we were to make it fair, this is part B, what would we change the $2 winnings to? Okay, so now let's reorganize what our expected value would look like. I told you that a 0 expected value is fair, so we want this to equal 0. We set up this equation here. Instead of the negative $2, we're going to have X dollars, obviously, because that's the one we're changing. Okay, the probability that he still wins is still 15 out of 36, and the probability that you win is still 21 out of 36. Well, now we just solve this equation for x. Okay, well, this is 21/36, so 0 is equal to 15/36 times x plus 21/36. Okay, subtract the 21/36 over, don't be afraid of fractions, negative 21/36 is equal to 15/36 x. Solve for x, you multiply by the reciprocal, so 36 over 15. What you do to one side, you do to the other. Okay, the 36 is canceled. That's why I told you to not be afraid of fractions. So negative 21 over 15 is equal to x. Now to convert that into an actual dollar amount, x is equal to negative 140. So if Senor Stemstato is only winning $1.40 each time, then this would be a fair game. But because he's winning $2 each time, it's obviously not a fair game. Okay? So let's learn why you should never, ever, ever play the lottery. Okay? In a lottery, 6 numbers are randomly chosen without repetition from the numbers 1 to 40. If you correctly pick all 6, you win $1 million. If you pick 5 of the 6, you win $1,000. If you pick 4 of the 6, you win $100. No money is awarded for picking 3 or fewer numbers. What is the value of a $1 lottery ticket? Seems like your golden ticket, right? You spend $1, you win $1 million, okay? Well, let's just see why lotteries even exist in the first place, okay? So we've got a bunch of different things going on here. You have to get all 6, right? You could go 5 out of 6. You could go 4 out of 6, or 3 or fewer. Okay, so those are the different possible outcomes for this particular lottery. All right, what's the payout? Well, if you get all 6 right, you win $1 million. Yay! Okay, well, if you win 5 out of 6, you get $1,000. Less yay, but still cool. If you get 4 out of 6, you win $100. Okay, well, what's the payout if you get 3 or fewer? Well, it's not 0 because you are actually paying your $1. So you are losing your $1. Okay, so again, this is in terms of you. This is a plus value, plus value, plus value. Those are good things. You want those. -1, you don't want that. Okay, now, tricky part with this one is actually figuring out the probability of each scenario. A little bit more complicated than it looks. The probability of getting all 6 right. Well, first of all, there are 40 numbers to choose from, and they are randomly choosing 6. That's a combination. Order doesn't matter. It doesn't say here that order matters. So 40 choosing 6 would be how many this is out of. To get all 6 right, you need to have 6 successes. And that means of the 34 non-winning numbers, you need to have 0 of them. A little hint, 34C0 is 1, 6C6 is 1. Okay, so the probability of actually winning is 1 out of whatever 40C6 is, which it's a large number. Okay, so that tells you how many different options there are in this game. 3,838,380. Okay. So to get 5 out of the 6 right, all right, you need to have out of your 6 numbers, 6 correct numbers, you need 5 of them. That also means that of the 34 incorrect numbers, you need 1. And that again is out of the 40C6. Okay, so all of these are going to be out of that 3,838,380. Okay. All right. So to calculate that, 6C5 is 6. 34C1, I'll give you a hint, that's just 34, times 6 is 204 ways you can get 5 out of the 6 right. Okay, so then you got to do 4 out of the 6, set up the same way. 6 possible right answers, you need 4 of them. It also means of the 34 wrong numbers, you need 2 of them. Okay, so 6C4 times 34C2. Okay, so now all of a sudden there's quite a few different ways that you can win $100. Okay, now the last one, 3 or fewer. Again, they group them all together, 3, 2, 1, or 0. You could calculate each of those individually and then add them up, or these are all the winning ones, which means anything else is a loser. So take that 3,838,380 and subtract the 3 winning totals. Okay, so 1, 204, and 8,415. And that tells you how many different ways you can lose the lottery. All right. So then to figure out what the expected value of a $1 lottery ticket is, you have to do payout times probability, payout times probability, payout times probability, payout times probability, add them all together. All right. And I just paused my recording there because I went ahead and just did the math myself to save some time. So when you actually do payout times probability and add them all together, your final answer ends up being negative 0.46. I mean, you could round to 5, but it really is irrelevant because we're talking money here. So essentially, each lottery ticket you buy, you're losing 46 cents on. That's how lottery ticket or companies make their money, and why they're able to offer a $1 million prize on the very, very, very rare chance that there actually is a winner. So that, ladies and gentlemen, is why you should never play the lottery.